Okay, so now we're going to have a look at the t-test. So the t-test, there are two different ones. There's paired and unpaired. We're going to have a look at them both. So they're in your book one after another, and I think they are both under lesson 2, but feel free to take 2 lessons to do them, or 2 hours worth of work to do them. So this is the first of the inferential statistical tests. So this is where we can use the word significance. We are comparing our value against a mathematically calculated value. So this is objective. We've actually got something to compare it to. We're not just comparing 2 values from 2 different studies. We're comparing it to a list of things called critical values. So we have more certainty with these values. We can be more certain that there is a difference, and so that's why we can use the word significant. Okay. So we're going to have a look at the t-test. We're going to have a look at the different equations. It gets quite complicated, but again, they give you the formula. The only thing you've got to remember is what the different parts of the formula mean. Now, before we get to the formulas, they look complicated. You are never going to be expected to calculate every part of it. It would take too long for the number of marks that they give. And so they will always give you some bits of it. Okay. So the t-test is used to compare means. So if you can't calculate a mean, you can't do the t-test. Okay. And that's something else that comes up quite often in exams. What test could you do? What test could you not do with this data? So one of the things to look for a t-test is whether or not you have means, because it compares the means. And it looks to see if there is a significant difference between the means. Are they, I mean, yes, there will be a difference, but is it a significant difference? Is it a big enough difference? Okay, now if there is a difference, there will always be a difference in biology. It's very random, you know, it just is. Anyway, so yeah, it's whether or not that difference is big enough. So we're going to have a look at unpaired and paired. Now, unpaired, as the name suggests, your data is not paired. So this is 2 separate groups of individuals, separate groups of organisms, separate groups of people doing different things. So you could have, the example on the PowerPoint here is treated and untreated. So if you'd used fertilizer on one field of corn and not used fertilizer on the other field of corn, the corn samples are different. If you did revision techniques with one class and didn't do revision techniques with the other class, they're not the same. So paired, it's the same individuals but in 2 test conditions. So for example, before and after exercise would be a good one for that. So the same people taking their resting heartbeats, then getting the same people to exercise, and then, you know, whatever, having a look at, I've lost my train of thought. So yes, the same people, a resting heart rate, and then get those people to exercise and take their heart rate again. Okay, cool. Right, so the paired t-test, your groups need to be the same because it's the same people. So you're comparing a mean from before something to after something. Unpaired, your groups can be different sizes. They do not need to be the same size. So one of the examples we're going to have a look at, there's 10 individuals in one group and there's 12 in the other group. So they don't need to be the same size. You're just comparing the means. So you need to be able to calculate a mean for that 10 group, and you need to be able to calculate a mean for the group of 11, but then you just calculate, you're just comparing the means. Yeah, they're just more examples, so you can have a look at those in your own time. Right, now with these kinds of statistical tests, when we can use significance, we work to something called a null hypothesis, or also known as H0. Now a null hypothesis always states that there is no significant difference. So no difference between your before and after, no difference between your treated and untreated. Okay? Now you can reject the null hypothesis. If you reject the null hypothesis, you're saying there is a difference. So for example, exercise does increase heart rate, but if you accept the null hypothesis, you're saying there is no significant difference. So for example, exercise does not increase heart rate. Okay, now mathematicians, if you reject H0, you then have to come up with some alternative hypothesis. You don't have to do that in biology. You accept or reject, and that's it. And that's because we're scientists. So if we're rejecting a null hypothesis, we go back to the drawing board. We've rejected one scenario, we then move on and have a look at the next one. And all we're bothered about is rejecting, because until you have sufficient data, you can't accept an alternative because you don't know what the alternative is. So we always just accept or reject, move on. The null hypothesis, that is. Right, so these are very complicated. So the hypothesis, chickens fed maize supplemented by lipid produce more male offspring than those fed maize alone. Null hypothesis, there is no difference between the number of male and female offspring of chickens fed maize supplemented by lipid and those fed by maize alone. All you really need to say is the feeding of, or the supplements, oh God, I don't know. There is no difference in the gender division in offspring from food. There are fewer slugs in dry areas. There is no difference between the number of slugs found in wet and dry areas. It's a bit more standard, really. But really, all you want to say is there is no difference between X and Y. Now, always relate it to the question. So if the question is talking about peacock feathers, you talk about peacock feathers in your answer. If the question is talking about number of strawberries on a cupcake, then you talk about number of strawberries on a cupcake in your hypothesis and then in your conclusion. So always relate it to the question. Can you tell two things that I happen to have on my desk? I have a cup with peacock on it and I have a cup with a cupcake and strawberries on it. Very sorry. Right, so the unpaired t-test, that's what we're going to have a look at first. So you've got two groups here, you've got treated or untreated. You could have a drug group and a placebo group. They are not the same individuals. On a drug trial, some of the patients get the placebo, some of the patients get the drug. And that would be exactly the right way to use a t-test. Okay, so two different groups of individuals. So we're going to have a look at an example. So 22 mice are divided into two groups, one of which is given a normal diet and the other is given a protein enriched diet. Is there evidence to suggest that the protein enriched diet increased the mass of the mice? So if you have a look at the table, we've got normal diet, protein diet. We have two different size groups there. That's absolutely fine. And they've worked out the mean. So they've worked out the mean increase in mass, and then they've worked out the standard deviations of that. And that's fairly typical of an exam question. You will be given some information because when I show you how to work out the standard deviation for one of these tests, it's flipping horrendous. So you will always be given some information. So what is the null hypothesis? Why don't you pause the slide? Don't move on to the next one yet. Have a look at what you would come up with. So our null hypothesis is that the protein diet does not increase the mass of the mice. There is no difference between the diets, is another really easy way of putting that. So you can see the null hypothesis doesn't have to be quite as complex as it was in that previous table. So this is the t-test. This is the which one are we on? Paired, unpaired. Unpaired t-test. This is the unpaired t-test. Now it looks horrendous. You have two of everything because you have two sets of data. So if I can highlight things, this is the mean of the first sample. Let me just rub that off because you can't actually see. So that's the mean. So this X bar thing, that is the mean of the first group, and then you subtract the mean of the second group. Now it doesn't matter which way around you get those. If you've got a negative number, you just ignore it, it doesn't matter. But you're just finding the difference between the two means. And it doesn't matter which one is the first group and which one is the second group, it's fine. So you work out what the difference is between the two means. Then let's have a look at these things. So you can see this S1 thing is the standard deviation of, oops, God, I can't highlight one thing, is the standard deviation of sample 1. So you will be given, most likely, the standard deviation. So the standard deviation squared divided by the number that's in the first sample. So N1 is the number that's in the first sample. And then you add that to, when you've worked it out, the standard deviation of the second group divided by the number in the second group. So the number in the second sample. So it's just to quickly recap, you divide the two, you subtract the two means, work out the difference between the two means, that's on top of the equation, and then these bits, you need the standard deviation divided by the number. So we had a group of 10 and we had a group of 12, did we? God, I actually remember. So you work out those bits and then you add these bits together and then you do the square root. You've got to remember to do that. Square root all of this stuff first and then you'll get a number and then you divide this stuff by that whole answer. Okay? Right, let's have a look. So if we had our sample size of 10 and 12, you can see that's where we've put our numbers there. So that is N1 and N2. Okay. Now on the top there, we've got our means. And so you can see we've got a mean of 20 and a mean of 18. So they are subtracted from each other there. And then we've got some standard deviations. So let's pick a different colour. So we've got standard deviation of 2.12, 1.78. And you can see they're put in there. And you square them. Now this is what the exam board want to see. They want to see you putting the figures into the equation. You can then just put all of this into your calculator and let your calculator work it all out. Okay, the more times you work out individual steps, the more error you introduce, rounding errors. So the exam board assume you know how to use a calculator, and that you have a scientific calculator, and that you will round at the very end. And on that point, most of the time, it will ask you or tell you how many decimal places to do it to. Okay, so once you've plugged all of these numbers into this equation, you can then just work it out. Now, what to do with that value? So once you have your t-test value, you need to compare it to something called a critical value. Now, critical values come in great huge books of them, and the mathematicians have probably seen that. In your exam, you'll just be given one or maybe two critical values to compare it against. So, as it says here, in statistical hypothesis testing, a critical value is the value corresponding to a given significance level. This cutoff value determines the boundary between those samples resulting in a test statistic that leads to rejecting the null hypothesis and those that lead to a decision to not reject the null hypothesis, which yes, doesn't make an awful lot of sense. So thankfully, I have nicely summarised it for you here. So in other words, it is the value at which you decide to accept or reject your null hypothesis. Is there a difference or isn't there a difference? So you have a look at your critical value, and if your value is less than or greater than, that tells you whether you are going to accept or reject. And in biology, it is always the same. Always the same. If your value is greater than the critical value, you reject. If your value is smaller than the critical value, you accept the null hypothesis. Okay? So that's all we want to know Are we accepting or rejecting? And we want to be confident doing that. You don't want a 50-50, I'm not sure if this is the right decision or not. You want confidence that you are making the right decision. So this is where probability comes in. So if the value of t is greater than or equal to the critical value, the difference between them is significant. So that difference that you might see between your data, it's just normal random variation. It's not a significant difference. Okay? So if your value of t is greater than or equal to the critical value, then you will be rejecting the null hypothesis. If your value is smaller than the critical value, then you will be accepting the null hypothesis. There is a difference, but it's just natural biological variation. So that is the summary, and this is all you have to remember. It is exactly the same. It doesn't matter what the test is. If it's greater than or equal to, you reject. If it's less than, you accept. So you need to remember this bit. Okay, so it doesn't matter what the test is. If it's greater than or equal to, you reject. If it's less than, accept. And that's the same for all statistical tests, which is what that just says. So probability. So this is an example of a critical value table. Now you'll notice up here we have things called p-values. Now these are probability levels. Now what you want to be doing is you want to be going, I'm going to accept my null hypothesis and I want to be confident doing it. So these give you a value and you compare, so let's just pick this one. You compare your value to this value, and if it's greater than, you will reject your null hypothesis. If it's less than, you will accept your null hypothesis. But these p-values are how confident you are. So if p equals 0.05, what you're saying is there is a 5% chance that you're wrong. So if you accept your null hypothesis, for example, at p equals 0.05, there's a 5% chance you should have rejected it. But that means there's a 95% chance you should have, whichever way around I just said that. Yeah, so you're accepting with a 95% confidence. So you are confident, 95% confident you should be accepting. There's only a 5% risk that you maybe should have rejected. And that's good enough. That's good enough for the vast majority of biology. If you get into clinical trials, you want to be moving up here because you don't want to run the risk of 5% of your population having ill effects or popping their clogs or something. Okay? So for biological systems, most of the time we work with 95%, which is p equals 0.05. Now, if you are given two critical values, so let's say, for example, you were given these two critical values here, and your value falls between them, then you will be accepting at one level and rejecting at the other. So what you're saying is you're between 95 and 99% confident. You are 99 and 95% confident, but you're not 99% confident. Okay, so that's what it would mean if you had two values. You would have two critical values. You would have to talk about both, and there are examples of this on later statistical tests in your booklet. So let's have a look. So it's about confidence. So the probability level is the probability of rejecting the null hypothesis when it's true. So you've said, nope, I'm rejecting the null hypothesis, but actually, oh no, it turns out you should have accepted it. That's what we're talking about. So for example, a significance level of p equals 0.05 indicates a 5% risk of concluding that a difference exists when there is no actual difference. So in other words, there's a 5% chance you are wrong in your decision. You should have accepted where you rejected, or vice versa. Okay, so a 5% chance of your conclusion being wrong, 95% chance that your conclusion is correct. So well done. So if p equals 0.01, there's a 1% chance that you're wrong and 99% chance that you are right. Okay, so it's just a measure of how confident you are that you're making the right decision. So those critical values are calculated for you. You don't need to know anything about them unless you do maths. So how confident are we that you should be rejecting the null hypothesis? How confident are you that you should be accepting the null hypothesis? And as I already said, I already talked about this, usually we're 95% confident. Clinical trials, you would want to be a lot more confident than that, and they usually actually work to 0.001. It's a very small chance. Right, so our t-value, back at the mice, worked out to be 2. Okay, so we need to know which of these critical values to use. So you'll notice here there's something called degrees of freedom. We need to work out how many degrees of freedom we have. Now the degrees of freedom is based on how many individuals you have. And for biology, it is always n minus 1. Okay, always n minus 1. So we have 12 individuals in the first group. So n minus 1 there makes 11. And then n minus 1 for the second group, where we had 10, gives us 9. So 11 plus 9 gives us a total degrees of freedom for our 20 individuals, of our individuals to be 20. So we had 22 individuals, so our degrees of freedom, n minus 1 for each group, gives us a degrees of freedom of 20. Now it says here minus 2, that's because they just added these together and took away 2 instead of doing n minus 1 for each group and then adding them up. Okay, so what we need to do is find 20. So there's 20, and we go along and we find 5%. 5% or 95% are the same thing. It's just if you are 95% confident, you're 5% not confident. So we end up with this value of 1.725. Okay, so we compare our t-value to that critical value. This is why we can use the word significant, because we are comparing it to something mathematically calculated. We're not just going, yeah, that standard deviation looks slightly different to that standard deviation. We're actually comparing it to something. So it says here, our t-value is greater than the critical value. So our t-value was 2. T-value was 2. The critical value is 1.725. So our t-value is greater than the critical value. So we reject the null hypothesis. We're saying there, so the null hypothesis was that there is no difference. We're rejecting that. So we're saying actually the difference does seem to have made a difference. But you would then want to investigate, is it the diet? Is there anything else that you've had a look at? Anyway, so our t-value is greater than the critical value. We'll reject the null hypothesis and we would accept, well, we don't have to accept an alternative. The diet has increased the mass of the mice. Okay, cool. Right, so you can have a look through those worked examples and then have a look at the questions. Some of the answers are on this PowerPoint. So have a look at these when you've had a go at doing them, and you can check your answers. Okay, so I'm just going to kind of flick through these because I just want to make sure I've covered everything. But there you can see here they've given you, oh whatever. Anyway, you can work through it. Right, what to include in your conclusion. So when you're doing a concluding statement, you always have to include all of these things. You have to include your value. You have to include the critical value. You have to say what p-value you're using. You have to say whether it is more than or less than, and you have to say whether or not you are going to accept or reject. Okay, so at p equals 0.05, our t-value of 1.21 is less than the critical value of 2.23, so we accept the null hypothesis. There is no significant difference between the old and new kit, and so that's what they've done here. They've related it to the question. Okay, so we're saying there is no difference between the old and the new kit. Brilliant. Okay, so let's move on to the paired t-test. Now this is where your test groups are the same people. So it's the same people, so you only have one group. So this is just n-1 because it's just one group. Okay, they're the same individuals. You do two different things to the same group. So the groups should be the same because you should be doing the same thing to all of those individuals. Okay? Right, now hold your horses a bit with this one. So this over here is for working out the standard deviation that you're then going to use in the t-test. Now, most of the time, every single time I've seen that, this has already been given to you. The standard deviation values have been given to you, but I thought I'd show you it anyway. So to work out the standard deviation for the t-test, you do the sum of the differences squared, the difference between the means squared minus, and look at this, this is where people go wrong. It is the number of individuals times the difference squared, the mean of the differences squared. So read this bit, please. Now, like I said, the vast majority, the only times I've ever seen these come up, you are given the standard deviation, okay? But just be aware that this is the equation just in case. So you would do the difference of the means squared minus the number of individuals in your group times the mean of the differences which you squared. So have a look at that there. Okay, that is divided by n-1, so the number of individuals minus 1, and then you square root the whole thing. Okay, but like I said, that in past questions has always been given to you. So let's have a look at the t-test. So this is the paired t-test. So this equation, you've got the mean of the differences, it's nicely being pointed to, and then you times that by the square root of n, so the square root of the number of individuals that you've got. So if you had 10 individuals, it would be the square root of 10 times the mean of the differences. Okay, so the mean of the differences, you look at the difference between your bits of data. So I'll talk to you about that in a minute. We'll have a look at an example and I'll show you what we mean. And then they're all divided by the standard deviation. Okay, so if you've got two sets of data, so let's say before a test and then after a test, before a test and then after a test, I don't really care what the test is, let's just have a look. So you work out the difference. So the difference between 10 and 11 is 1. The difference between 9 and 10 is 1. I mean, that's nice and easy for myself. And so this is the mean of the differences. So you would add these two up and divide by how many there are. So 1 plus 1, thankfully, is 2. 2 divided by 2 gives you 1. So that's what my mean of the differences would be. Obviously, that's too simple an example. So let's have a look at an example. So you can see here we've got some data. And so this is what we mean. So these two bits of data, you would work out what the difference is between those. You would then work out what the difference is between those. You would then work out what the difference is between those. You'd work out what the difference is between those, etc. Okay? And then once you've got all of these differences going all the way down here, whatever those differences are, that's when you then work out what the mean is. Okay? So that's the mean of the differences, which is why they call it that. That's terrible. Okay, so a student was investigating the effect of exercise on heart rate. She recorded the heart rates of a group of volunteers at rest and after skipping for 3 minutes. So the mean difference between the resting heart rate and the heart rate after skipping was 52.5 beats per minute. Now, if you want to, you can work those out and see if you get the same value. And the standard deviation of the difference was 8.2. So in other words, this value varied by 8.2. So 8.2 up, 8.2 down, if you're doing one standard deviation, for example. So as you can see in this question, you have been given the mean of the differences and you have been given standard deviation. So then you just plug it into your equation. So the degrees of freedom is n-1. same as it was before. So you've got 8 pairs, so the degrees of freedom is 7. The null hypothesis is that there is no statistically significant difference between the mean heart rate before exercise and after exercise. Okay, now you can see we've got the mean of the differences here. We've got the number, square root of the number, so the number, we've got 8 pairs, and then you divide it by the standard deviation, and we were given the standard deviation. Okay, so then you end up with this value of 18.11. Okay, and again, this is showing you're working. You put the numbers into the equation, you then just put it all into your calculator. So you have to write this on your exam paper to get one of the marks. Right, so the critical value at p equals 0.1 in this particular question, that's what they used. I just got this from somewhere, so we'll go with it. With 7 degrees of freedom is 3.499. So we had 7 degrees of freedom because we had 8 individuals, 8 test subjects. So n-1 gives you 7 degrees of freedom. So you would look this up in a critical table if they gave you one, or sometimes they just give you the critical value. So if your critical value is 3.499, then our value, our calculated value, was 18.11. So that's a lot higher than the critical value of 3.499. So the difference is significant. Okay, so what we're saying is because our value is greater than the critical value, we are rejecting the null hypothesis. Now, the null hypothesis said there was no difference between your resting heart rate and your exercise heart rate. What we're saying is there is a difference. So there is a significant difference between the mean resting heart rate and the mean heart rate after skipping. So we're going to reject the null hypothesis. Okay, hopefully all that makes sense. So again, you can have a go at completing the examples. It gives you a little clue here for question 3. Assume heart rates is paired and the Ibis is unpaired. It gets very, very, very complicated and it's not very obvious from the question. Those questions are not from the exam board. I stole them from somewhere else. I can't even remember where I stole them from actually. Just online somewhere, I think. Okay, so have a go at the questions. If you get stuck, try phoning a friend, see if they can take you through it. Otherwise, don't forget to use the Q&A sheet and I'll have a look. You can always, if you're completely stuck, photograph your book, photograph your working, send it to me and I'll see if I can figure out where you've gone wrong. Okay, so if you just email me that one, I'll try and figure out where you've gone wrong. So we've got clearly some answers. So pause, complete the questions before you move on.